Year 11, this is the first video for this new chapter on intermolecular forces and allotropy. I'm going to talk through about molecule shapes, which is the first section that we got here. So a lovely picture of an iceberg there. And why I chose the picture of an iceberg is ice is one of the examples of a molecule that in its solid state it is less dense than its liquid state. So most substances have a more dense solid state than their liquid state, but water is one of those exceptions to that. Another common exception is ammonia, and hopefully we'll learn about why that is throughout the course of this chapter. Okay, so our inquiry question for this chapter is the same as last one, I think it was. What binds atoms together in elements and compounds? So I talked about, that's specifically talking about intramolecular bonds, those bonds within a molecule, intra. Now we're going to start talking about looking at those bonds within the molecule, those intramolecular bonds, and starting to look at the intramolecular bonds or intramolecular forces. They're the forces of attraction and repulsion between two differing neighboring molecules, or more differing neighboring molecules. Okay, so there's our outcomes, but again, I will highlight that yellow section there. I'll use those syllabus dot points throughout there. I might go a bit thicker with this pink. Okay. So, the form of attraction between molecules is the intermolecular forces there. That's why I put it in highlighted there. I also did the inter in italics because inter and intra are so similar in wording. So, these intermolecular forces determine many physical and chemical properties of molecules. So, knowing and predicting these intermolecular forces allows us to predict these properties such as boiling points, melting points, solubility, density, and many more. These are skills that are going to last you throughout the course and you don't want to forget them. Okay, so the path that leads us to determine these intermolecular forces between molecules starts with what we were studying just before, electron dot structures, and also our knowledge of electronegativity and bond polarity that we were looking at last chapter. So we're going to build on those again. So let's start with predicting the shapes of molecules. So the syllabus dot point is investigate the differences between ionic and covalent bonding by examining the spectrum of bonds between atoms of varying degrees of polarity with respect to their constituent elements' position on the periodic table. A lot of words, but we did that last chapter. Okay, this second point, modeling the shapes of molecular substances. Not many words in this one, but a very big concept. Okay, let's have a start. I've got some images of some molecules here. I've got there ball and stick structures. Ball, stick, that's why it's called ball and stick. And I've got their structural formula here as well. So this one is sulfur hexafluoride because we've got 1, 2, 3, 4, 5, 6. And here's the ball and stick model with the sulfur in the middle and the fluorines around there, sulfur hexafluoride. Below that we've got water, which you'll see is a bent molecule, and we'll learn why in this chapter. And carbon dioxide, which is a linear molecule. It's all in a straight line with these double bonds, and we'll learn why it's that shape as well. So, having an easy system to determine the shape of molecules will allow us to understand why certain molecules have certain properties. And there's a theory that works really well with a set of rules that gives quite accurate predictions. Especially for all the molecules that we're going to look at during the course of the HSC course, this valence shell electron pair repulsion theory works really well. Okay, so remember, I've got down here, we're talking about molecules, so we're talking about two or more non-metals bonding to each other covalently. and they're not forming an ongoing network solid. Okay? So let's look at valence shell electron pair repulsion theory. Valence shell electrons, those electrons in the outermost shell. Notice they come in pairs. We're going to treat them as pairs. And repulsion theory. So it's saying that these electrons in the outer shell come in pairs and they're going to repel each other. All right. Next slide goes through two premises. The two premises of this VSEPR, I forget these letters around. I think most chemists actually call it VSEPR theory. So is it, yeah, that's a like a little moped, but yeah, let's just call it VSEPR theory. So the two premises: one, electrons mainly come in pairs, and they're going to be either lone pairs or bonding pairs, okay? A lone pair, remember we talked about with Lewis dot structure, was a pair of unbonding electrons. They weren't involved in the bonding at all. And remember when we were drawing those covalent bonds, it was always two electrons that were going into a single bond, and another two electrons that are going in there to make a double bond with 4 electrons, and then another 2 to make a triple bond, so it would have 6 electrons. So electrons tend to come in pairs when we use this model. Okay, so we can call each of these pairs, so each of these bonding pairs around a central atom, as a bonding group or a bonding region. Okay, we're going to use that language for VSEPR. So this bonding group term that we're going to use, and we're going to count these bonding groups, the criteria for a bonding group is either it's a lone pair of electrons, or it's a single bond, or it's a double bond, or it's a triple bond. And we're going to count these. So the second premise is the locations of these electron pairs are in a sphere around an atom, and because they have the same charge, a negative charge, they'll want to be as far away from as each other as possible, because electrons repel each other. So we're considering a 3-dimensional sphere, and these electron pairs will want to repel each other and get away from each other as much as possible around that sphere. Okay, these two postulates simplify everything we've learnt about electron behavior, from the Schrödinger model about electrons being waves and kind of probability shells and all this kind of crazy stuff. It simplifies it so much, but we still get very accurate results. So we can still use these to predict the shape of molecules, and when we use instruments in chemistry to look at these shapes of molecules, because we can see the light coming off them, it's actually really accurate. It does a really good job. So a simple physical model that these postulates can be made, can show, a simple model is grouping of balloons together. And I try to do this in the classroom, but here we'll do it in video, and I found this nice image online. So the more and more balloons that are crammed around a central point, they kind of push away at each other equally. So here with 2 balloons, there, oh, it's not staying there. Oh, because I'm using the eraser. Let's change. Oh, let's not do red. Let's do green, so it's the opposite. So here we're kind of, in our model, we're saying that the atom lies in the center here. And we've got 2 bonding regions, and they're repelling each other equally, just like the balloons are pushing each other away equally. And you get a nice linear molecule where they're 180 degrees away from each other. Okay? Here with 3, we get this model where 3 are pushing each other away, but they're kind of in the same plane, the same circle. So they're basically 120 degrees away from each other. When we get 4, things become more interesting. You add 1 to the 3, and it pushes the original 3 down from that one up top. So it's no longer in a single plane, but it's truly in 3 dimensions. And we'll learn that that's called tetrahedral. Now, when you get a 5 around that central, they kind of, you get 3 in a plane around the outside, and then an up and a down. And then when you have 6, you get 4 in a plane, and then you get an up and a down there. So this model with balloons works quite well about showing these shapes in 3 dimensions. Okay, so a procedure for VSEPR. Okay, what you need to do first, number 1, is to draw an electron dot structure or Lewis structure of the model, like our example of water here, where you got 2 lone pairs and you got your 2 bonds, oxygen to hydrogen there. So first step, Lewis structure, and we did that last chapter. Second step is we need to determine how many bonding groups there are around the central atom, and determine the basic shape of the molecule. And sometimes this is called the basis. So here with the oxygen, the central atom there, we've got 2 lone pairs and 2 single covalent bonds. That means there's 1, 2, 3, 4 bonding groups. And that means it's this 4 tetrahedral shape. Okay, it's got a tetrahedral basis. There's 4 bonding groups repelling each other equally around this sphere. Number 3 is determine how many non-bonding electron pair groups you have, which are like gaps in your actual shape. Okay, so here in this diagram to the right here, we have oxygen and hydrogen, but we've actually got 2 lone pairs up here that are contributing to the shape of the molecule, but they're not actual bonds. So the basis is tetrahedral, but because there's 2 gaps in it, we just have this actual molecule here, what we can see and where the atoms are. And that is why water is, when we actually see the molecule, not that we can see it, but we can detect light from it, it has a bent shape like this. So use the number of bonding groups versus the number of non-bonding electron pairs to determine and describe the final geometry. So it's a basis of tetrahedral, but the final shape is a bent shape. Okay, so that's our procedure, 4 steps, 1, 2, 3, 4, that we'll use for all molecules. And I'll do some examples, but let's talk more about the shape here. Okay, so if you've got two bonding groups around the central atom, they're going to be 180 degrees apart. Okay? Predicted bond angles, 180. If you've got 3, they're all going to be in the same plane, and they're going to be 120 degrees apart. But they're all in the same plane. They're equally pushing away from each other around this central atom here. Once you get 4, it pushes the 3 original down, and you get it going in this kind of pyramidal shape or tetrahedral shape. Tetra means 4. A tetrahedral shape. And that was the basis for water back there. And here's the balloon projection of it, the balloon model of it. Okay? When you get 5, it's called trigonal bipyramidal. It's got 2 pyramids with a triangle base, and 2 of them, so 2 pyramids of triangles, trigonal bipyramidal. When you have 6, it's called octahedral, because you get this square kind of shape in the middle and then the top and the bottom. So 2 pyramids, but with square bases. We could call that quadrilateral bipyramidal, but we don't. We call it octahedral because the shape that it makes actually has 8 faces of triangles, octahedral. Okay, so these are the bases shapes for 2 to 6 bonding groups in there. So these are the 3D shapes that we need to consider for step 2. These are the basis shapes. They could also be our final shapes. It just depends on how many of these bonding regions are actually lone pairs. Okay, one thing we need to tackle too is how do we represent on a 2-dimensional surface a 3-dimensional shape, which we're going to need to do because some of these are planar. They're good to draw 2-dimensionally, but once you get to tetrahedral, you're going to have problems because it's a 3D shape. So when we draw these, what we tend to do to show some 3-dimensionality in our molecule is to use what we call wedges and dashes. Now, when we're considering, I've given an example here of the molecule methane in these 2. Methane has a formula of CH4. You can draw a Lewis structure to see why. Carbon has 4 valence electrons. Hydrogen has 1. They'll share 1 electron in each bond, and so carbon has its 8 and each hydrogen has its 2. But the trouble is, with our normal structure, we draw it like this one here. And the thing is, this suggests that there's 90 degrees. There's a right angle between these bonds, and there's actually not. It's a tetrahedral shape. There's 109.5. Is it 109.5? I think it's around there. 109.5 degrees between each of them, and it's in 3 dimensions. So between each of them, 109.5 degrees. So this kind of representation here is kind of a bit wrong, because it's kind of assuming that they're 90 degrees and the molecule's planar. It's not true. So what we do is we use these dashes and wedges. Let me change color. Notice this guy and this guy, okay? This one here and this one here are our normal bonds. They're saying, hey, I'm in the plane of the page. But if we do that, if we have two of the hydrogens and the carbon in the plane of the page, one of the hydrogens must go behind the page, and one of them must be coming out of the page towards us. And what this solid triangle or wedge is saying here is that it's coming out of the page towards us. And this dashed one is saying, I'm going back into the page here. So it's showing some 3-dimensionality. So as it says here, these 3 bonds are in the plane. This one's going behind, and this one's coming out ahead. And that's how we show some 3-dimensionality in these molecules. It's really handy, and it's try to get away with doing this 90-degree thing. It is kind of easier in shorthand, but when you're giving your final answer in the HSC, you need to show all your understanding, and you might want to start using dashed and wedges for those 3 dimensions. Okay, so there's a little bit of skills that can help us show these 3 dimensions on a 2-dimensional surface. Alright, here's a nice grid representation that I really like for the possible final molecular shapes, based upon the number of bonding pairs to the number of lone electron pairs. Okay, so let me talk you through it. Let's choose purple, because why not? Okay, when you've got 2 bonding regions, there's only one possible molecule that it can have, because they can't have any lone pairs there. It must be 180 degrees apart from the central atom, and we call that linear. Okay? It can't have any lone pairs on that central atom. Okay, when we get 3 bonding regions, we've got 2 possibilities. One here is, this one here, is where we have 3 actual bonds, and that's called trigonal planar, and that's where we get plane, 3 of the atoms arranged pushed 120 degrees apart from each other, all the way around. But we can also have 3 bonding regions and 1 lone pair. Okay, so we don't actually see that lone pair. What we do see is the central atom and these 2 other bonds, actual bonds, forming a bent molecule at 120 degrees apart. Okay, so that lone pair is still taking part and pushing those other 2 down, so it's 120 degrees apart. We call that bent. And maybe you want to say bent 120 degrees too, because we're going to come across some other bent molecules at different angles. Once we have a basis of 4 bonding regions, we have 3 possible shapes. They're all on the tetrahedral basis. So if we have 4 bonding regions and 4 actual bonds, like we did with methane, they're all 109 degrees away from each other. And we see it as an actual tetrahedral shape. But sometimes we can have 4 bonding regions but 1 lone pair. And so what we actually do is we get a molecule with these 3 actual bonds pushed down because of this lone. So it's like in a pyramid, and it's called a trigonal pyramid. Notice it's not bipyramid, it's just a trigonal pyramid. And they're bent down, and they're still 109.5 degrees in the actual bonds there, but you don't see those lone pairs. We could have a tetrahedral basis also with 2 lone pairs, and we talked about this already with water, where we don't see these lone pairings, we just see that central atom with these 2 bonds, and it's also called bent. But notice the angle difference, 109, I think it's 109.5 degrees. So there we get our bent molecule. So when we have a tetrahedral 4 basis, but 2 lone pairs, just like water. Okay, when we have 5, I'm back on my eraser again. When we have 5, we have 4 options. We can actually have 5 bonding regions with 5 actual bonds in there. And we get this trigonal bipyramid shape that we discussed earlier, where they're all arranged equally away from each other. So, up and down 90 degrees away from each other, but around this central part, they're 120 degrees, like the trigonal planar earlier. Okay, when we have 1 lone pair in there, we kind of get, it's sometimes called a seesaw shape. We just actually see this up and down and one side, but not this top part here. And it's called a seesaw usually. Now, when we have 2 lone bonding pairs, we actually get this all in the single plane T shape. And they're 90 degrees away from each other. So we call it T shape. And when we have 5 bonding regions but 3 lone pairs, we get a linear molecule, just like this one up here. A nice linear one. Okay? Now let's consider our 6 bonding regions. When we have 6 actual bonds, it's called octahedral. But when one of them is lone pair, it keeps that octahedral shape, but we just get the central ones around that plane and the one down. And we call that a square pyramid, because it's a square through these 4 and projected up to a pyramid. Where there's 2 lone pairs, they oppose each other, and we just get a molecule that is actually all in the same plane and is in a square shape. So if you're looking down from the top, it'll just look like a T. But not the same as this T shape. I was just considering why it's not called a T. Different T. So here again, when we've got 3 lone pairs, we get another T shape. Okay? 3 lone pairs, 3 actual bonds. And when we have 4 lone pairs, we get another linear molecule. All right. Here, on this next slide, I've just used my molecular modelling kit, which we'll play with. We've got some at school, but I just used my one at home. And I made examples of them and have taken photos for them. So I hope you find that helpful too. It's good to see them in actual kind of 3D shapes. All right. So let's look at some examples here, and these ones are all from the textbook. So beryllium chloride, there are only 2 pairs of electrons around. The most stable arrangement for 2 pairs of electrons to be diametrically opposed to get a linear molecule, okay? I know here, and we haven't really discussed it, beryllium's still happy here with its 2 4 electrons. Because it will just fill up the s orbitals. So with beryllium and boron, they don't have to fill up their full octet. They can just fill up some s orbitals or p orbitals. They're a bit weird. So beryllium chloride has 2 bonding regions and 2 actual bonds, so it's a linear molecule. Boron trichloride, notice that the boron only has 6 electrons there too. It's one of the exceptions too. It can be happy with it. 6, it just puts them in the p orbital and forgets about the s orbital. But back to the shape of it, it has 3 bonding regions and 3 actual bonds. So 3 bonding regions, 3 actual bonds, it's trigonal planar. Okay, all in the same. So it's 120 degrees away from each other. Now we're moving up to a tetrahedral, and we've talked about methane here. We've got 4 bonding regions and 4 actual bonds, all opposing each other. So in 3 dimensions, this should be drawn with a wedge and a dash that we've got 4 actual bonds, tetrahedral basis and tetrahedral shape. Okay. Here we've got ammonia, which has a tetrahedral basis because it's got 1, 2, 3, 4 bonding regions, but it's only actually got 3 actual bonds. So it's going to be an example of your trigonal pyramid, okay, as your final shape. Now let's look at water here. Water also has 4 bonding regions, 1, 2, 3, 4, but it has 2 lone pairs. So its actual shape is a bent, and it's 109.5 degrees from each other, okay? So here is some, electron dot structures. We've got methane, we've already talked about that. And we've got ammonia here, we've already talked about that. Here's water with its 2 lone pairs. Here's a different one that we haven't considered that has the same thing happening as water. And that's dihydrogen sulfide, or it's often called hydrogen sulfide, H2S. Notice the central atom here has 2 lone pairs and 2 actual bonds, so it's still going to be tetrahedral basis, but with 2 lone pairs it's like water where it's a bent molecule. So here on the right I've drawn the shapes of these. Methane, tetrahedral, ammonia, tetrahedral basis, but it's a trigonal pyramidal. Water is bent at 109.5 degrees, and hydrogen sulfide is also bent at 109.5 degrees. So same shape for that molecule. Here's a table from the textbook talking about these in a tabular form and giving some examples of each too. They may come in handy later. And here's a nice diagram of each of the basis shapes from the textbook too. Okay, this is another representation of this without my scribble all on it. And it's got some nice information there. This was produced by some people or a person, and they run a website called compoundchem.com. You might want to check it out. They make really handy infographics for chemistry like this. They're very pretty and give very good information too. Could be good for studying. So check that out. And also check out, I've do some more examples in this video. That one was produced by me. One of my first videos there. And also we've got Tyler DeWitt going through a few. We've got intro to VSEPR theory, practice problems, and common mistakes of them. And I will put in this one here, which is a Professor Dave one. Professor Dave's always really good too. Notice Tyler DeWitt's actually using some polystyrene models here too. Does a great job, so check them out. Okay, I think that's all for the first video. I'll start on polar bonds to polar molecules in the next one. Thanks for your time, guys.